Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to gravitation. So in this video we are going to discuss about another important concept related to gravitational force acting on an object, which is Newton's shell theorem of gravitational force. So far we have discussed the basic universal law of gravitation is that the gravitational force of attraction between two objects of different masses m1 and m2 separated by a particular distance r between their center, it is given by F is equal to g m1 m2 by r square. Okay, directly proportional to the product of the two masses, inversely proportional to the square of the separation distance. G is the universal gravitation constant. Now, what the shell theorem does is that it tries to give us the magnitude and direction of the gravitational force acting on a point mass due to a solid sphere or a spherical shell, in which the mass distribution is homogeneous, it is uniform. That is the density of mass density of the solid sphere and the spherical shell, it is uniform, it is constant throughout. So suppose we have a point mass present at a distance outside the sphere or inside the sphere or inside the spherical shell, what will be the nature of the gravitational force? Okay, so here the important thing is that the spherical shell or the solid sphere which is under observation, it is of uniform mass density. The mass distribution should be uniform, it should be homogeneous. Now there are two cases here. In the first one, the point mass is present outside the solid sphere or spherical shell, and the second case we have the point mass present inside the spherical shell or sphere. So we'll discuss the first one, where a point mass, small point mass of value small m, it is present outside the spherical shell. So we have a spherical shell of total mass capital M, okay, and it is of uniform mass distribution. The mass density is uniform, it is homogeneous. Now the point mass is present at a distance r away from the center O of the spherical shell at location P. Now here what the shell theorem says, what is the theorem? Says that if a point mass lies outside a uniform spherical shell or sphere, so we are discussing first the shell, then we will discuss the sphere. It applies for both. So if a point mass lies outside a uniform spherical shell or sphere with a symmetric uniform internal mass distribution, that is uniform mass density, the shell or sphere, it attracts the point mass as if the entire mass of the shell or sphere were concentrated at its center, and the gravitational force acting on the point mass, it acts towards the center of the shell or sphere. So here what it says, that here in case of this spherical shell of uniform mass distribution, the gravitational force F acts in a line which is towards the center of the spherical shell, and the spherical shell behaves as if the entire mass of this shell is concentrated at its center. It is, it is present at the center. That is the concept of point mass. So that's why we discussed in our field characteristics of gravitational force, the gravitational force of attraction, it is applicable only for point mass, and is a central force. It is a central force, that is, it always acts along the line joining the center of two objects. That's why here for the point mass, the uniform spherical shell, the gravitational force of attraction tries to attract the point mass towards the center of the spherical shell, as if the entire mass of the shell is concentrated at the center. The gravitational force, it acts towards the center O of the spherical shell. So if we join this, the force and this by a straight line, it will be in the same direction. It will coincide. The force vector and this line, it will coincide. And the magnitude of this gravitational force, it is equal to G m capital M small m by r square, which is the basic universal law of gravitation formula. The spherical shell is of mass capital M, the point mass is of mass small m, they are separated, their centers are separated by a distance r, and this is the thing, by r square. And here another important thing is that the point mass is present far away, so where the displacement is much greater than the radius. So here this formula is applicable if the displacement small r is greater than the radius of the spherical shell, radius is capital R, or it lies on the surface of the spherical shell, okay, on the circumference of the spherical shell, greater than or equal to R. This formula is applicable. So when it is present on the surface of the spherical shell, the small r will become capital R, GMM by capital R square. Okay, so this formula is applicable if the point mass is present outside the spherical shell or on the spherical shell, just on the circumference of the spherical shell. Okay, not inside. It should be on or outside. Okay, this formula is applicable. Simply direct the gravitational force is directly proportional to the product of the two masses and inversely proportional to the square of the separation distance between their centers. Similarly, here, if we replace this spherical shell with this solid sphere, okay, it has a mass of capital M, it is of uniform mass distribution, uniform mass density, it has a radius of capital R, and the point mass P is present at a distance small r away from the center O at point P. Okay, here also, as per the shell theorem, which is applicable for both the spherical shell and sphere, solid sphere, the gravitational force acts towards the center of the solid sphere O, as if the entire mass of the solid sphere, it is concentrated at its center. Okay, the gravitational force acting on this point mass is towards the center of this large solid sphere. Okay, and the value of the gravitational force, it is also the same expression, that is F is equal to G product of the two masses M, capital M and small m by R square, okay, inversely proportional to the square of the separation distance. And same here, if the separation distance is greater than the radius of the solid sphere or equal to it, that is, the point mass is present just on the surface of the sphere, this formula is applicable. Okay, so in the case of both spherical shell or solid sphere of uniform mass density, the gravitational force acting on a point mass is always directed towards the center of the solid sphere or center of the spherical shell, as if the entire mass of the shell or entire mass of the sphere is concentrated at the central point. Okay, this is accordance to the characteristics of gravitational force, which says that it is a centralized force, it is central force. It acts along the line joining the center of the two objects, and it is applicable for point masses only. So point mass is a concept, as I said, that where it is visualized that the entire mass of the body, it is concentrated at a certain point. So for spheres and shells, it is easy to visualize because the center of mass is at the center of the shell or the sphere. Okay, so this is the shell theorem for spherical shell and sphere. Now, why does it happen like that? Why the gravitational force, it acts in line along the center of the shell or sphere. So the reason is that suppose we divide the entire spherical shell into equal parts. Okay, we take small portions of the spherical shell. In this case we have taken two portions, two mass portions on the spherical shell, which are located on symmetrically opposite points here, symmetrically opposite points, and both these have same mass. Okay, they have same mass. As the mass distribution or mass density is uniform, both these equal portions, they will have the same mass. So each of these portions will exert gravitational force of attraction on this point mass. Okay, what we are trying to visualize is that the entire spherical shell is divided into a number of such small portions. Okay, this portion, this portion. Likewise, we can divide it into many portions. Okay, here like this, and symmetrically opposite point this. Again here this, and symmetrically opposite point this. So we can divide the spherical shell into a number of such small portions, and they will all have equal masses because the mass density is uniform. Now here we are considering only this one and this one, and all of these should be present in symmetrically opposite points. Okay, now both these points, mass portions, they are at the same distance from the point P, okay, small a, because they are present in symmetrically opposite points. So these portions, they will exert gravitational force on this point mass. Okay, these small mass portions, let there be F. Okay, it will act along these directions. The gravitational force exerted by these small mass portions on point P. Both these forces will be the same, the magnitude will be the same, because the mass are equal, the mass portions are equal, but they act along different directions. Now these forces, these two forces, they will have their vertical components and horizontal components. Now the vertical components of this two forces, they are in vertically opposite directions, one towards the top, other towards the bottom, whereas the horizontal component, it acts along the same direction, that is towards the center. So the vertical components being equal in magnitude but opposite in direction, they cancel out each other, whereas the horizontal components, they get added together. Same thing can be done for these two portions, these 2 points also. Okay, this point and this point, there will be a force, okay, like this. Okay, this force and this force. Now both these forces, they will be equal in magnitude, they will have a horizontal component and vertical component. Okay, now the horizontal components, again they will add together, they will get summed together, whereas the vertical components being equal in magnitude but opposite in direction, they will get cancelled out. Okay, same thing goes for these portions also. So the trick here is to divide the entire spherical shell into a number of such small portions and consider only the two portions which are present in symmetrically opposite points on the spherical shell. Okay, symmetrically opposite points. And if you see, the total gravitational force because of the spherical shell is the summation of the gravitational force because of these small portions, and all of these small portions will have their horizontal components, summed together, whereas the vertical components being cancelled, and then the net gravitational force will only have a horizontal component, which will always act along the line joining the center of the spherical shell to the center of the point mass. Okay, this is the reason. Same thing can be done for solid sphere also. Now the entire solid sphere, it can be divided into a number of such small portions which are present at symmetrically opposite points. Okay, both these points, they have the same mass because the mass density is uniform, they are identical portions and they are present at the same distance. Okay, magnitude wise they are present at the same distance away from the point mass P. So the magnitude of the gravitational force capital F, it will be the same, but it will be in opposite, different directions. So here again, these two forces, they can be resolved into their horizontal and vertical components. Again, the vertical components of these two forces, they will cancel out each other because they're equal in magnitude but opposite in directions. One towards the top, one towards the bottom. Whereas the horizontal components, they are along the same line towards the center. Okay, it is directed towards the center O. Similarly, here also the entire solid sphere can be divided into numerous such, okay, symmetrically opposite small portions, okay, like this. They will have same masses, okay, and they will exert forces on point P where their vertical components will cancel each other out and the horizontal components will get added together, and the net gravitational force acting on the point mass P will always be directed towards the center of the sphere, okay, from the center of point mass P towards the center of the sphere O. And that is the reason why whenever a point mass is present outside a shell or a sphere, the net gravitational force acting on the point mass due to the shell or sphere always acts along the line joining the centers of the two bodies, okay, because of this reason. Okay, so this is for point mass present outside a shell or sphere. Now what if the point mass is present inside a shell? So the theorem says that if a point mass is present inside a spherical shell with a symmetric mass distribution, homogeneous internal mass distribution, the gravitational force on the point mass is 0. Now the simplest explanation for this is, suppose we have a point mass present here, okay, at the center, let's say, for the easiest explanation. Now this point mass will be attracted towards different directions if we divide the entire spherical shell into numerous such small portions, okay. Now if we pick any two symmetrically opposite points, let's say this one, okay, let me use a different ink, okay, this 2 points. Now both of them, they are of the same mass, okay, let's say capital M, just I'm saying, and this is small m, point mass small m. Now these two portions, they will attract the point mass towards each other, and the gravitational force with which they will do so, it will be the same, G capital M small m by r square, because they are at the same distance away from each other, the point mass. Now both these forces, they will be equal in magnitude but opposite in direction, okay, equal in magnitude, opposite in direction, so they will cancel each other out. Similarly, let's say these 2 points, okay, capital M, the masses are capital M because the mass density is uniform, identical portions present at symmetrically opposite points, they are at the same distance away from the point mass P, and they will exert equal forces on the point mass but in opposite direction, so they will cancel each other out. Same thing happens here also, okay, equal magnitude forces in opposite directions, they will cancel each other out. Same thing happens for these two symmetrically opposite points, same mass separated by same distance from the point mass. exerting equal forces in opposite directions, and it will cancel each other out. Now the same principle is applicable if the point mass is present anywhere, okay, anywhere if it is present, the same principle is applicable. The vertical and horizontal forces, they will always cancel each other out. The horizontal and vertical forces, they will always cancel each other out, and the net force acting on the spherical shell, it will be 0 when it is present inside the shell. This is only applicable for spherical shell. Now, if the point mass is present inside a sphere, a solid sphere, then the situation is different. So, for the point mass present inside a solid sphere, the theorem is different. It says that if a point mass is present inside a homogeneous sphere with homogeneous uniform mass distribution, then the gravitational force, it is exerted by the portion, this portion, which lies interior to the point mass. Okay, so let's say here the point mass is present here. Okay, let's say this is the total radius of the sphere, capital R, and the point mass is present here, where the radius of this much portion is R. So here the gravitational force will be exerted by this portion only, which lies interior to the point mass with radius R, radius small r. This much portion will not exert gravitational force. This portion will not exert gravitational force. The black highlighted portion will not exert anything. Only the white portion will exert the gravitational force, which lies interior to the point mass. So that's what this theorem says, that if a point mass lies inside a uniform homogeneous sphere with a symmetrical homogeneous mass distribution, the gravitational force is exerted by the spherical mass portion which lies interior to the point mass, that is this white highlighted portion, the white highlighted portion, not this black portion. And the gravitational force will be directed towards the center. It will be directed towards the center, as if the entire mass of this portion of the sphere is concentrated at the center. Okay, this is the concept. Now, how it will happen? See. So, here the mass of this portion, this highlighted portion, the white portion which lies interior to this point mass, that is equal to 4 by 3 pi r cube, that is the volume of this inner sphere, the volume of this inner sphere, this is this much, 4 by 3 pi r cube, this is the volume of the inner sphere, and this is the density of the sphere, which is uniform, which is constant. Okay. Now the mass of this inner sphere is equal to 4 by 3 pi r cube, which is the volume of the inner sphere into density. Okay, and the gravitational force between the point mass and the mass of the inner sphere, which is given by this, F is equal to G m subscript r m by small r square, because the entire mass is visualized to be concentrated at the center for this inner sphere. So here, instead of capital M, we are using m subscript r, which is the mass of the inner sphere, inner spherical portion. We are not considering the mass of the entire sphere. We are not considering this. We are considering this, the mass of the inner sphere. So that is why this theorem becomes very important. So whenever a point mass is present inside a solid sphere, the portion of that sphere which lies interior to the point mass, the inner portion of the sphere coinciding the point mass, only that highlighted portion exerts gravitational force. This outside portion, the portion lying outside the point mass, that is the black portion here, that does not exert gravitational force. The gravitational force exerted by that portion is 0. Only this inner highlighted white portion exerts gravitational force, and that's why the mass of that portion only is considered. Here the mass of this, the volume of this inner sphere is 4 by 3 pi r cube. When we multiply it with the density of the sphere as it is uniform, we get the mass of the inner sphere, and only that mass is used here. F is equal to g m subscript r small m by r square. Okay, so this is the shell theorem of gravitational force. Now it will be very much, we will apply it when we'll use this concept to find out the gravitational force because of Earth and the acceleration due to gravity because of Earth at different points. Okay, so this is the shell theorem of gravitational force. Okay,